In this video, the ORACLE and Attentive ORACLE methods are outlined. ORACLE is a deep learning-based method for collision-free navigation of aerial robots. The approach relies on a supervised learning step that allows to predict if a certain candidate motion primitive shall be in collision or not with the environment. The method makes no assumption for access to a map of the environment or reliable position estimates and only considers access to a partial robot state, an immediate depth image and a 3D goal vector pointing to the destination, alongside a list of candidate actions based on motion primitives. As a partial state, the method considers the linear velocities of the system, its roll and pitch angles as well as the angular velocity around its z-axis. Exploiting these inputs, the method builds a collision prediction network, or CPN, that explicitly focuses on robustness against uncertainty. Specifically, both aleatoric and epistemic uncertainty is considered. Aleatoric uncertainty, in this work, refers to the prediction uncertainty due to the covariance over the partial robot state. To that end, we are using the unscented transform to sample further sigma points, and inference takes place across the mean of the robot's partial state and the remaining sigma points. Epistemic uncertainty relates to uncertainty in the learned neural network models, among others because of the difference between real and simulated depth data. This is captured by means of a deep ensemble of neural nets that assemble the collision prediction network. Exploiting the deep ensemble and the multiple sigma points from the unscented transform, the method arrives at a collective uncertainty-aware collision score indicating the likelihood of a certain action primitive leading to a collision or not. This uncertainty-aware collision score is calculated in parallel, exploiting modern GPU capabilities, for each action sequence in the motion primitives library. Considering the top-performing primitives, meaning those with least expectation to lead into a collision, the method then further considers the goal direction to pick the one leading safely towards the desired direction. Importantly, ORACLE is extended to not only perform collision-free flight but also attend towards areas of visual interest. Through Attentive ORACLE, the method further exploits a mask over the depth image that encodes which areas are salient for the robot's mission. This may be the output of a visual saliency method, a method for object detection, or any other bottom-up or top-down motivation. Exploiting this further input, the method trains an information gain prediction network, or IPN, that scores each motion primitive regarding how well it optimizes a utility metric of information gathering. The latter is trained in a supervised manner considering a privileged expert that has access to a volumetric map onto which the areas of interestingness have been projected. The results of this IPN are combined with the collision prediction outputs of the CPN in order to identify the next best action sequence that allows the robot to navigate towards the desired direction, while simultaneously performing implicit information sampling efficiently.